And so, John, take the stage. It's all you.
All right, cool. I guess I'll go ahead and skip the introduction section here. The main objective for this lesson was to, as per the title, right, new perspectives on quantum annealing. So what exactly do I mean by new perspectives, right? Quantum annealing has been around for a while, and it seems like there's no like what I would consider like a fresh twist on the topic. But the thing that I think is important is to make a distinction between the fact that there's the gate model. So if you guys have used, I bet you guys are familiar with IBM Qiskit and Google Circ, Penny Lane, they all revolve around the gate model. And it's a very simple model to understand, where you start with some initial quantum state, then you perform some number of quantum manipulations, we would call these gates, and then you perform a measurement at the end to get your calculation. But kind of on the outskirts of the quantum computing scene, there's always been this, I guess I'm willing to call it the underdog here, because it seems to be kind of pushed out of the way by the popularity of the gate model, which is quantum annealing, or I'll just abbreviate it as QA for short. And part of the reason is QA is more of what I would call D-Wave. D-Wave is I guess, almost the de facto company for quantum annealing. They promote this method of performing quantum computing. So I just call it D-Wave. And it operates on a very different scheme than the gate model does. But what I'm hoping to motivate today is to kind of recognize what this quantum annealing model is good for, what are some of its drawbacks, because I think one of the important things as you guys learn more about quantum computing and you become sort of quantum mechanics or quantum engineers yourself, is to realize that the same tenets of engineering still apply. So one of the things that I always focus on, or that I always teach, is you want to find the right tool for the right job, right tool for the right job. And yes, I know my handwriting is pretty atrocious. This has its roots back in high school, but but the idea here is, I'm trying to show that there are certain problems that quantum annealing may have a more natural expression for, but at the same time, I want to make it very clear what the known benefits of quantum annealing are and what the drawbacks are. Because a lot of times when quantum annealing gets brought up, they don't really talk about the fact like, oh yeah, there are certain, there's like a certain number of asterisks up next to it, indicating like, well, there's some technicalities in terms of how you would characterize performance here. We're uncertain about this. This seems promising, but is unconfirmed, so on and so forth. And as I do this, I want to throw in maybe a couple problems that are related, that are naturally expressible on quantum annealers, and these are problems that I'm hoping are a little more unique and maybe arguably more interesting than you would normally get introduced to. So I'm trying to avoid the standard introduction, which is like, oh, I'll give you max cut or some variant of like the traveling salesman's problem. These are they're not bad examples, but at the same time, they're ones that I'm trying to provide a new spin on. So that's kind of the goal, is to get you guys to learn more about what quantum annealing is, what it's like relative to the gate model, how it works, and then some applications for it. And oh yeah, if there are any questions that pop up, I do have chat open here. Oh, here we go. May she have any questions? Yeah, by all means. Thank you, Tanisha. Yeah, if you have any questions, feel free to drop them in chat or raise your hand. As I said, I've been doing this for 2.5 years, so I know, well, the Zoom part's a little more recent since the unfortunate dawn of the pandemic, but I'm pretty comfortable with using Zoom for these lessons. So I'm going to go straight out of the bat. I'm going to make a claim to you guys that the gate model and the quantum annealing model are technically computationally equivalent. So what I mean by computational equivalence is that the problems you can express in the gate model are equivalent to the like you can compute the same problems you would on the gate model. They can be mapped to quantum annealing, but the way D-Wave pulls this off is a little suspect. It's not. It is not the way D-Wave does it is not universal. And if you don't know what I mean, like when I'm throwing around the term universal and like, oh, they're equivalent, I'm actually going to do that for maybe the first 30 minutes of this lesson is prove this kind of computational equivalence. But first, let's kind of let's kind of get into the idea of where this quantum annealing idea comes from. And usually the way it's centered around, especially in physical implementations, is what's known as the Ising-Hamiltonian. And once again, we know the Hamiltonian is just the it's a very nice physical way of describing the setup of a certain. It's a very nice mathematical way of describing a certain physical setup. So, for example, you've probably heard of like the harmonic oscillator, or well, I guess it's a bit of a claim. I'm saying you've heard of it, but the basic idea is that you can have the kinetic energy and the potential energy. So the factors in your system that would contribute to the kinetic energy and the potential energy, and you'd have this sum, and then you have your Hamiltonian here. And a lot of times in quantum computing, when we are trying to find a solution to a certain problem, the gut instinct, kind of like the de facto way of representing and solving a problem, is we translate it to this Hamiltonian format. The Hamiltonian somehow, there are a myriad of ways of doing this, somehow gets onto the quantum computer, and then we try and find the ground state. So the Hamiltonian can have many discretized energy levels. So this could be energy 0, energy 1, energy 2, and usually our solution is encoded as whatever configuration of our quantum state will give E0, or the lowest energy level. But the Ising-Hamiltonian, even before we get into the quantum mechanical side, it has its roots in sort of classical physics. Like, it's not something that it only exists in the quantum realm. It comes purely from classical mechanics. And what I'm going to draw some math here. And don't fret if it seems a little alien. I'll give a perfectly reasonable and hopefully a friendly intuition as to what's going on here. Sigma n, and then this would be, let's see, I equals 1, and then h sub I, s sub I. So before I even jump into the math, I want you to think, I'm going to give you a physical model that the math should go with. So I want you to imagine kind of a square grid, if you will. It's something like if you use graph paper for homework, right? So you'll see like all these nice uniform squares all connected to each other. Now, on this network of squares, if we look at the areas where each of these squares seems to be connected, we can put a dot there just for illustrative purposes. But each dot that I'm drawing is considered what we call a spin. Spin is a very it's a purely physical idea. Unfortunately, the name spin is a bit of a misnomer. That has its origins in the fact that one of the reasons why quantum mechanics came to be was because in the early 19th century we had some issues with the fact that there were problems in physics that could not be explained with the traditional framework. In fact, there's that infamous quote from Lord Kelvin, which is actually not from Lord Kelvin. It's from his student, but it gets attributed to him. And he makes the rash claim that there is nothing more to be discovered in physics. All there is more and more precise measurement. And as you can see with quantum computers and the advent of quantum mechanics for the past century or so, there's been quite a lot of new stuff that's been found, and still more to be found. But I digress. We don't actually have to worry about spin here. Just think of these as like little bar magnets, like like the same magnets you put on your fridge, or on the same magnets in your speaker. These can be thought of bar magnets with like a North Pole and a South Pole, and they can all be oriented in a certain way. But then these lines can represent an interaction. So, for example, I can define some value for this interaction, but if I were to say rotate, and now I'm really abusing the physical terminology here. If I were to rotate this magnet in a certain way, then it would influence its neighbors, these neighboring kind of magnets here. And I guess it is worth explaining what spin is, even though I'm attempting to abstract away from it. Spin comes from the fact that in classical physics, the problem was the electron, particles like the electron have some electric charge to it, but they also have a little magnetic field around it. And if you were to try and calculate the, because usually with Faraday's laws, when you have a spinning electric charge or a moving electric charge, it creates a magnetic field. And the problem is, if you try and use traditional physics to calculate how fast the electron has to be spinning to create its own magnetic field, it's faster than the speed of light, which seems to break, a lot of traditional physics. So that's why it was originally called spin. In reality, the electron is not, just like rapidly spinning on its axis. It just has an intrinsic kind of magnetic field. And you can have any, and by the way, electrons aren't the only things that have spin. You can have nuclei that have spin, and even larger macroscopic things that have spin. And the idea is that we have a physical setup where you have all these spins in this grid formation. And what I'm saying here is that one spin and then another spin have a defined level of interaction between each other. So that's what I mean by the edge here. So for example, you could have the case where maybe if one spin is spin down, then the other one wants to kind of go the other way. And if one spin is spin up, then it wants to go spin down. Or you can have the exact opposite case where they both want to be aligned in the same orientation. So if one of them wants to be up, the other one wants to be up. And you can kind of see, if you mess around with this a bit. Oh, and this term, by the way, is for each individual spin can have its own initial bias. So maybe it starts out wanting to be more spin up than spin down, or spin down than spin up. But this turns out to be a tricky thing to calculate certain dynamics for. And in fact, what was I trying to think of? Oh yeah, sometimes you get cases where we call it gets magnetically frustrated. So what I mean by magnetic frustration is I can give you a very simple case here with maybe 2 spins, and then I have another spin here. And this, we might define it in such a way that this spin always wants to be opposite to its neighbors. But maybe in this edge says like, look, you should be opposite to your neighbor, but this spin says you want to be equal in orientation to your neighbor. So now the problem occurs that this guy gets the actual physical term is frustrated. It can't seem to be happy. If it's spin up, it's not going to be ideal. If it's spin down, it's not going to be ideal. So it becomes it has this kind of frustration. This is like a consequence of this phenomenon. But this is known as the Ising-Hamiltonian. And there's a quantum mechanical equivalent. So this is actually usually the non-quantum equivalent of this problem is you can have magnetic moments in, say, a piece of metal, but you can also go to the quantum level and you can assume like you have a bunch of nuclei or a bunch of electrons in this configuration. And even for like D-Wave's hardware for quantum annealers, what they actually have is a bunch of flux qubits. So like it's a very similar architecture, I would argue, to what you might see in traditional superconducting quantum computers, like what IBM and Microsoft do. But they also have it laid out in a pretty similar format. So the only difference between the physical traditional Ising-Hamiltonian and the quantum Ising-Hamiltonian is that these spin values, which I just kind of define as S sub I and S sub J, are now replaced by our friend, the Pauli Z operator. The Pauli Z operators are all quantum mechanical, but the same structure for the formula essentially holds. So that gives us this kind of a quantum mechanical Ising-Hamiltonian. And the idea behind using the Ising-Hamiltonian in quantum computation is like, hey, if we can encode a certain problem in this Hamiltonian format, and as I mentioned earlier, if we can find the lowest level energy of that Hamiltonian along with its associated state, so which spins are up and which spins are down, then we can find the solution to certain problems. So it's kind of nature's way of doing this. And in fact, the motivating argument for using this method or this Hamiltonian is like, hey, if we have these quantum annealers, there should be it should arguably be faster than what a classical computer can do. Although, as I'll show a little later, there's a bit of a this is still a contested matter. In fact, D-Wave for a while, and I'm not trying to like dunk on him or give it a hard time, but that's just the plain fact is that for years D-Wave had a lot of skepticism over like, are your computers really quantum? Are they actually exploiting quantum phenomena? And even Scott Aronson, who used to be with the Simons Institute, now he's with UT Austin, he came up with some pretty compelling arguments against it. And a lot of people gave him flack saying like, oh, you're just a quantum skeptic. And then, he had to come up with a number of blog posts saying like, look, I'm not here to hate on the quantum computer. I'm just here to say like, I will believe your claim once you can give me conclusive evidence that there is this speed up. So, as you guys go more and more into the quantum computing space, you come to realize there's a lot of spicy stuff that goes on in this field. But I digress here. So with this Ising-Hamiltonian, before I go to the quantum annealing argument for this, I will try and make the transition to quantum annealing a little gentler here by pointing out that this kind of Hamiltonian is really friendly. It's super friendly for VQE. So you could use your existing gate model, and if you've heard of the variational quantum eigensolver, what you can do is you can take the same Hamiltonian that I showed here with the Pauli Z operators. And in fact, all you have are Pauli Z A, Pauli Z B, and then Pauli Z. So you have a single and you have paired Pauli Z operators. You can put these on VQE and you can find a solution that way as well. But this is kind of cheating, right? Because I said I was going to cover quantum annealing, not the gate model. But I do want to point out that you can take what current quantum annealers, such as what D-Wave offers, are good at, and put it onto the gate model and still get the same answer. Although in terms of comparing performance, I'm going to be honest, even I am not too well versed in that. And in fact, there are a number of difficulties in benchmarking the difference between the difference in performance between quantum annealers and normal quantum computers. And in fact, I'm going to later on, I'm going to switch the screen share to several papers that I've found that I think would be great reads for all of you in the audience. These are papers that I've found incredibly readable myself. They don't assume a lot of prior knowledge, and which point out like, hey, trying to compare performance is actually it's very hairy business, because you want to make sure it's a very fair comparison, but at the same time, there's so many moving factors that the comparisons are tricky to pull off. Oh, and by the way, I should mention this whole, like, if you want to see the actual VQE implementation, there's a paper by Abhijit, Quantum Algorithm Implementations for Beginners. That's a paper by Los Alamos National Laboratories. So that's actually a really good read. But now that we know this kind of Ising Hamiltonian, sort of the classical origin and the quantum origin for it, we can actually get into the quantum annealing, the definition of quantum annealing. Now, quantum annealing this is something I want to make very clear. And if there's one thing you take away from this lesson, I certainly hope it's this. Quantum annealing is related to adiabatic quantum computation. And now I realize I'm really starting to throw like these big words around, but it's nothing unusual. Quantum annealing is actually what we would consider a looser definition. So quantum annealing is a looser definition of adiabatic quantum computation. And in fact, let's see, yeah, there's a paper by Vinci and Lidar from 2017 entitled, non-stochastic interactions in quantum annealing via the Aronov-Anida phase. Don't worry about what that stuff is. Whenever I give lessons, I try to be very explicit about my sources. And the idea here is that AQC is a way of doing quantum computation that quantum annealing comes from. And quantum annealing is essentially just a looser, AQC has its own definitions. And if we loosen those definitions for adiabatic quantum computation, you get quantum annealing. So that begs the question, what is adiabatic quantum computation? And that will help me and hopefully you understand where quantum annealing comes from. Adiabatic quantum computation comes from a remarkable proof in quantum mechanics, which looks like the following. So if I were to provide h sub s is equal to 1 minus sh sub 0 plus sh sub 1. So what is going on here? Oh, and I should mention that this s here, so this s ranges, or should range from 0 to 1, and usually it's something like tf over t, where t is like a total time constant, and then tf is the time, like time as it goes on, as it progresses. So that's literally the definition of S. But what this adiabatic principle, so that's the name of this phenomenon in quantum mechanics, what the adiabatic principle is claiming, or actually has been proved, is let's say we come up with a quantum system that's defined by a certain Hamiltonian h sub 0. And it's a very simple Hamiltonian, arguably something that's easy to set up. And what happens is if we start in the ground state, so we're in the ground state, G sub s, or a GS of this Hamiltonian, and over a period of time, by linear interpolation. So if you guys have done, if you guys ever have done like stuff with graphics before, a linear interpolation is something that comes up. But the idea is you'll notice that as time goes on, this value becomes closer and closer to 1. So S goes from 0 to 1. This Hamiltonian starts to vanish. It just kind of slowly vanishes, and then we transition over to this other Hamiltonian h sub 1. And the idea is that if we start in the ground state of this known Hamiltonian, and we do this slowly enough, in fact, that's the physical term, adiabatic. Could you mention the papers you just mentioned? One on the AQC Los Alamos, and the other, yes. So the first paper that I mentioned is from Abhijit. I'm probably saying the name wrong here, but I can give you the title, and it's Quantum Algorithm Implementations for Beginners. It's not a very unique, and it's a little misleading of a title. Whether or not I would call it for beginners is subject to how much background you have in quantum computing. Although I imagine if you guys have signed up for a lesson in quantum annealing, you're probably fairly well versed. So that's the first paper. And the other one that I wanted to mention, the other one is not a very friendly read, and that's non-stochastic interactions in quantum annealing via the Aronov-Ananda phase. So that's Vinci and LiDAR, 2017. Oh, and by the way, the formulation for this guy, I should probably just put the author down. It's also by LiDAR. This is Albosch and LiDAR, and this came from their 2018 paper for adiabatic, and it's just titled Adiabatic Quantum Computing. And that's, let's see if you'd like me to interact with you more, only if it works for you though. Oh, okay. Yeah. Gotcha. Yes. Thank you, Tanisha. So, I mean, hopefully, yeah, I mean, if you have any questions, by all means, just feel free to bug me. And I mean, I can stop. I understand I'm throwing a number of different moving parts here, but my goal is that near the end, these moving parts will come together and there'll be a reasonable explanation for what's going on here. So, and by the way, I cite this paper. This is a review paper. It's literally just called Adiabatic Quantum Computation. But this definition is not unique to that paper. Like every other paper on quantum annealing will use the exact same formulation, maybe a minor variation in the variable naming, but essentially the same thing. But the idea with adiabatic quantum computation is that we want this we want to start in the ground state of this Hamiltonian, and then with some period of time, t. And by the way, this t is kind of this t is also a bit of is dependent on the energy levels in your Hamiltonian, or in the problem Hamiltonian. So in fact, I think the gap, so between the lowest energy level and the first excited energy level of the Hamiltonians, this t is dependent on this gap here. And I'm not going to go into too much depth. In fact, I'm not going to claim to fully understand or provide an excellent explanation for what exactly is going on here. But yeah, basically the idea with adiabatic quantum computation is like, look, H1 is the sort of the problem Hamiltonian. So that's where that's where we encode our problem. And in this case, it can be this Ising Hamiltonian. So we can take the Ising Hamiltonian in its quantum form as kind of the problem Hamiltonian, remembering that the way you configure the interactions between spins can represent a certain problem, which I'll show how to do that soon enough. But then you also have a kind of ground state Hamiltonian. So this is just some very trivial, something that's easy for you to set up. And with some period of time, we can evolve from the ground state of this to the ground state of the problem Hamiltonian, recognizing that we've encoded our problem properly to the point where the ground state of this problem Hamiltonian should be the solution to our problem. So is everything making sense so far, or am I going too fast? Or by all means, if any questions, feel free to drop them in chat. I know. Once again, my background is in mostly teaching college students. But I understand, community has an emphasis on high school students, which is fantastic, by the way. That one math class be like, yeah, that's a bad habit of mine. I know I'm doing like, I know the trend, right? You close your eyes for like 2 seconds in math class, and then boom, like the whiteboard has like 10 million more equations. But no, yeah, if you have any questions, put it in chat. I'm monitoring the situation here. So that's adiabatic quantum computation, and one of the assumptions with AQC is that it's adiabatic. The adiabatic part of it just means that we're doing it in some slow manner. So you can't just choose an arbitrary time and then say like, here's the initial Hamiltonian, and then bam, just jump to the final Hamiltonian. It's not how adiabatic quantum computation works. It has to be done slowly, and there is in fact a way to calculate an upper bound for that time. So hence why we use the term adiabatic. Once you get to like, I don't know if they teach it in high school, but I know if you get like your college level courses in physics, learn about like the adiabatic in context of thermodynamics, and you have an adiabatic process. But one of them is that it has to be this kind of slow, controlled evolution. And the other requirement is that it has to be isolated from the environment. So AQC is assuming like, the environment is not an interfering matter. But quantum annealing kind of throws that out the window. And it says like, well, what if we're not adiabatic? What if we're not perfectly isolated from the environment? then it doesn't really count as adiabatic quantum computation. One other thing I would like to stress is that quantum annealing is in general associated with, oh, I should probably erase this, is associated with CO problems. So CO is an abbreviation, not from me. It's from another paper I'll show a little later. It's associated with combinatorial optimization problems. So combinatorial optimization is it's just a class of problems. It's not a complexity class. So if you have a background in computer science, or if you've stuck around quantum computing long enough, you'll know like P and NP. It's not that. CO is an even broader generalization of problems where the input to your function, or like when you are you can call it that. The input to your function f of x is kind of discretized. So normally, like I can give an example. I guess gosh, I still have nightmares from my my IB math course. But if you have like the integral of a certain function. Usually, the example they gives they're continuous functions, right? So x could be any value from negative infinity to positive infinity. Is there a question? Sorry. Oh, I guess someone's not.
No, sorry.
Oh, you're good. You're good. Usually the inputs to these functions are infinitely continuous. So I could put in 0.1 or 0.01 or 0.0001. Whereas for combinatorial optimization problems, your domain is restricted and it's a discrete domain. So one of the best examples I can give is usually there's the classic example. Every computer science course will teach you this. So hopefully, if many of you guys are going into college, already in college studying computer science, you will touch on or you have heard of knapsack. And the idea of knapsack is like I have literally a backpack. You can think of a backpack, and this is why I never really pursued art. You can have a backpack, and you have a number of objects that you want to carry in the backpack. So maybe you have this big box that's a big box, maybe a smaller one, or maybe this really long box. They have an associated volume, right? So volume 1, volume 2, volume 3, they're going to take up space in your knapsack. And you, as maybe a courier, you want to make sure that for each trip you're making with this knapsack, or maybe a postman, is that you want to make sure you maximize the value. So what I mean by value is that each package here has some dollar amount associated to it. But the problem is it's not that intuitive. Like this massive package might only be $1, but this tiny box might be worth $100. And this, this very elongated box could be worth, say, $50. So you have a countable domain or a number of discrete configurations that your input can take. And depending on how you arrange your configuration, so for example, maybe I guess the optimal case is like, let's say V2 and V3 perfectly add up to the volume of my backpack, then this would be like an optimal solution. So it's combinatorial optimization. It's a combinatorial of the inputs here. So that's what we mean by CO problems. So quantum annealing is really targeted towards these CO problems where you have some discrete number of possible inputs. They're countable. It's not like a standard function where it's like 0.01 and then 0. Like there's an infinite number of things you can plug in. And in fact, I want to give one of the examples one of the really cool things. I think this was done by a company. I want to say it was, Protein Cure. I think it was Protein Cure. So this is a paper. If you look up this company on Google Scholar, I think you can find the original paper. But they use quantum annealing. So they use QA for the problem of protein folding. Protein folding. So the way, so now hopefully, if you're taking like high school bio, this should click. In fact, this will probably click better for you guys because the last time I took biology in high school was 6 years ago. So the basic idea is for when proteins first start out, they're not all like folded up already. In fact, they're just a really long chain of these amino acids. And the amino acids have different behaviors, right? Some amino acids like maybe attract others and some don't want to be next to each other, and some are hydrophobic and some are hydrophilic, some like water, some don't like water. And as a result, over time, like this protein will will fold into some very non-trivial geometry. And this is a very computationally hard thing to do. And even for like our best supercomputers, right? This would take ages to pull off, especially as that protein gets longer and larger in complexity. So what ProteinCure did is they converted this protein folding problem into something a quantum annealer is happy with. And one of the things you're gonna point out very quickly is you're going to realize, well, wait a minute, where is the combinatorial part of this? This seems like an infinitely continuous problem, right? Because like you can imagine like my arm here, if you're looking at the video stream, my arm here is maybe like 3 amino acids. The angle of rotation that protein can fold on is pretty much almost infinite. I mean, it's like it's a sphere essentially, right? 360 degrees of rotation, and then my arm here as another amino acid gives another degree of rotation. So it seems like there's no way you can get this on a quantum annealer. But what the team at ProteinCure have done is this rather bold assumption is they simplify the problem, and they do what I call, this is what I call the term. I don't think this is the proper term for it, but it's known as discretization. Discretization. What I mean by discretization is like you can have an infinitely continuous domain, and instead you kind of chunk up that infinitely continuous domain. So you can see like chunk 1, chunk 2, chunk 3. So what they did is instead of assuming like this protein is on a 3-dimensional space with all this infinitely possible rotations, they confine the protein to a 2D grid. And then they further simplify it by saying like, look, this protein, this amino acid likes to be with these amino acids, but not the other ones. So really, it just becomes this discrete. So it can only rotate like at 90-degree angles. Now you're going to ask, is this even accurate? I forget what the conclusion of the paper. So this is more like a proof of concept. But the idea is you should take, if you have a problem that's maybe infinitely continuous, there are ways to chunk it up quite cleverly and get the quantum annealer to be happy about it. Although the thing you should remember is with discretization, it's a bit of an approximation, right? You're losing some degrees of freedom. Although, the idea is hopefully as D-Wave or maybe even another company cranks more and more powerful quantum computers, we will be able to have a greater degree of freedom in this discretized space. So this is something I want to hopefully add to your toolkit of solving problems with quantum annealers. So hopefully that example seems to make sense with quantum annealers and kind of combinatorial optimization. Oh, and sorry, the reason now this brings me back to like, why did I bother bringing up the Ising Hamiltonian at all? So why was this mentioned in the first place? And it's because the Ising Hamiltonian is pretty much a shoo-in. Like a lot of problems in the quantum annealing domain can be naturally expressed as, sorry, blooper reel. Let me roll back on that one. There are a lot of interesting computationally hard problems, like what we would consider NP complete, that you can express in the form of an Ising Hamiltonian. And the D-Wave has built this quantum annealing hardware that naturally accepts some formulation of this Ising Hamiltonian onto their hardware platform. Now, one thing I want to clarify is AQC has no restrictions. AQC doesn't care what the Hamiltonian is. It doesn't, at any point in its definition, it does not say it must be an Ising Hamiltonian. On the other hand, for quantum annealing, pretty much all the implementations that I've seen for QA are based on the Ising Hamiltonian. I don't think QA is like married or specifically tied to the Ising Hamiltonian, but they pretty much go hand in hand. And one of the reasons for the appeal of the Ising Hamiltonian is there's another problem expression called QUBO, a quantum unconstrained binary optimization problem. So the binary optimization being your variable can only be 1, meaning yes, or 0, meaning no. And this seems really restrictive, because it's almost like asking if you had a problem. Now you're telling yourself like, oh, well, shoot, I have to express this in terms of some yes or no formulation or combination of yeses and nos. But it turns out to still be pretty expressive. And the only difference, in fact, is remember the poly Z operators have eigenvalues of +1 and -1. In QUBOs, you just have like X variables that can either be 0 or 1. And you can translate between the two, between a QUBO and an Ising Hamiltonian. And it's only, it's one operation. It's a very trivial operation to do so. And I've done a lot of my work with if and only if, a small startup here. I work with QUBOs pretty frequently. And QUBOs are a lot more natural to work with because they're just mapped to 0 and 1 versus +1 and -1, which is just a natural consequence of quantum mechanics. So that does bring me to one thing that I do want to warn about is, I showed AQC, and AQC has been proven to be equivalent to the gate model itself. So has quantum annealing, or rather, AQC is equivalent to the gate model. And in fact, that comes from a paper. Let's see if I can find it here. Not Lucas here. Diamant, the complexity of. Let's see, Hamiltonians. Give me a second here. I know I'm taking a little bit of time here. I have 15 minutes left, but I'd rather get it done in 10 minutes and make sure that I have time left over. Equivalent. Yes. Okay. Yes. The adiabatic. Yeah. So it's by let's see, Aronov's 2008 paper. I should probably put that down. Let's see, Aronov, 2008. So they actually did the math and showed like, hey, the gate model is equivalent to the adiabatic quantum computing model, but there's an issue here where quantum annealing, if we only use the Ising-Hamiltonian is not expressive enough to perform universal quantum computation. And that's I think that's Lucas 2014. I want to say is the paper for that. I think that's because I have I have a number of citations interspersed here, but I think that's the paper you'll want to refer to. But the idea is that the Ising-Hamiltonian, even though we have a hardware implementation, we can do quantum annealing on it, does not not every algorithm from the gate model is translatable to the Ising model and therefore runnable in modern quantum annealing hardware. So that's the distinction. One of the distinctions I want you to take home with today is the reason quantum annealing is not really as popular as the gate model is because they're not even as of now with current hardware, they are not equivalently powerful. Although there is a proof here. It's going to over time. So, oh, okay, cool, Tanisha, thank you. Let me go ahead and do a new share here. Okay, cool. So I don't have the gosh, I didn't pull up the paper, but there's a way to modify the Ising-Hamiltonian such that you saw the terms where sigma z's, they're just a bunch of sigma z's. If you introduce a sigma x and then a sigma z, so there's an x-z interaction, that's actually just enough to become a universal Hamiltonian. So that brings it up to the level of equivalence as an Ising-Hamiltonian. Shoot, I don't have the paper on me, but that does bring me to kind of the near the end part of what I wanted to show here, which was what does this QUBO exactly look like? Quantum unconstrained binary optimization. Okay, so here's the actual if you want to. This is once again a fantastic paper to get started with using quantum annealing and the kind of quantum unconstrained binary optimization format. And just the point I want to drive home, right, is we are looking at expressions like this. So you see these x1s, x2s, and then you have pairs, so x2 times x3. This can be mapped. This can be mapped to the Ising-Hamiltonian, and then you can have a quantum computer that naturally handles the Ising-Hamiltonian, and you can do some interesting problem solving there. And you can have an example here for max cut. So max cut is the idea you have this graph here, 1, 2, 3, 4, and 5. And the goal is to split up the vertices here into separate groups, but at the same time, you want to separate them such that you cut the largest number of edges. So what you'll do in building your Hamiltonian is you'll say well, hey, if I have an edge, edge 1 and edge 2, and maybe and they're on the same set. So once you've cut them, they're on the same side, and they turn out to not cut an edge, then there's kind of a penalty there. And you don't want to do that. So you see here, it says maximize. You want to get the largest possible value from it. So in this case, it'll tell you it is equal to 1, then exactly 1 of x of I and x of j equals 1, which implies that the edge is in the cut. Otherwise, it's equal to 0, and the edge is not cut. So when you are engineering these Hamiltonians, you're almost thinking in terms of energy levels, right? The lowest energy should give you the solution. Although I recognize this is maximized, I think later on in the paper, they say like just slap a negative sign on this and it becomes a minimize, essentially. So when you're engineering problems for quantum annealers, in general, you're trying to engineer something that will get to the lowest energy possible. And yes, okay, this is something I wanted to show you guys. This is coming from a fantastic paper. If you want to learn even more, and this explains it way better than I can. Perspectives of quantum annealing. Did I steal the title for this talk from this paper? No, but I stumbled upon this today, actually. If my talking seems to be a little incoherent today, it's because I just pulled an all-nighter, and I still have work to do on that all-nighter for senior design. If you guys are going to college and you're studying computer science or any form of electrical engineering, I think you'll have to do a senior design project. And at that point, I guarantee you'll have an all-nighter. But there are some caveats that I wanted to point out. I mentioned D-Wave, right? D-Wave has the quantum annealing hardware, but it's not exactly a perfect model here. So, despite the remarkable engineering achievement, it remains unknown if the D-Wave annealer, and this paper came out in 2020, by the way, or quantum annealers in general will afford quantum advantage for general class of problems. So there's some limitations, short coherence times. So this we can't blame D-Wave for, right? That's just the name of the game. We're always wrestling with coherence times in quantum computers. If any of you have studied error correction, you'll know your T1 and T2 coherence times. If you don't know what that is, hopefully I'm priming you for that terminology. Limited connectivity, I skipped the image, but just like how the normal IBM quantum computers, like you have a two-dimensional surface, right? There are graphs, like connections that you cannot make because you're going to have wires that overlap. And I guess we're not at the point where we can do that just yet with the superconducting quantum computing hardware. And we also have you see this funky word here. It's like stochastic, but spelled with a Q, stochastic. Stochastic refers to a class of Hamiltonians, like the Ising Hamiltonian that I saw with like just the two poly Z's interacting. And they're not considered universal Hamiltonians. So in fact, there are actually certain instances where it's equivalently easy to simulate it on a classical computer. So if it's easy to simulate on a classical computer, then that kind of means like there's not really much to look for in terms of quantum advantage. But this points out like the fact that we only have ZZs means we're kind of in a pit. But there was another paper that I read, and I kind of regret not having put the citation clear on my notes here. Once again, if you saw my writing on OneNote, you'll know my handwriting is pretty atrocious. But there is a paper that shows like you can still have just these two-term interactions, like just two quantum operators interacting with each other, but you need an X. So you need an XZ, and then a ZZ and so on and so forth. And that's considered like a universal. Whereas with the ZZs, not powerful enough. And by the way, I think the XZ was in the context of like pure adiabatic quantum computation. So if that was brought into the realm of quantum annealing where things are not as clean, that's not as adiabatic, not as isolated from the environment, things get kind of hairy. Yeah, see, look at, I mean, the authors of this paper, at the time of this writing, it's not known if remedying these limitations will practically lead to quantum advantage, but addressing them is a good place to start. So I don't know what the D-Wave team is thinking of. And in fact, if some of you, if you guys watch like, not watch, but monitor like LinkedIn, like there are all those like quantum news outlets. I know I have an actual problem with like LinkedIn addiction. I think I check it like 30 or 40 times a day. The Quantum Daily, I think, mentioned like a while back, a couple months ago, that D-Wave is also trying to make gate-based computers. Now, I don't know about you, but when a company that has been doing one method for like a decade decides to like say like, oh yeah, we're also doing like the gate model, but we're not giving up on quantum annealing yet. That's a little, that makes me a little uncomfortable, especially as someone that's done a lot of work in the quantum annealing space. I certainly hope it's a method that will continue to be viable for future quantum engineers such as yourself. But as is the case with quantum physics and math and science, if it's proven that there's literally no benefit, well, then kind of, that's something you just got to live with. It's just a natural consequence. Oh, and I mentioned all these NP complete problems that you might want to check out on the quantum computers. So in computer science history, there's a guy named Karp, and Karp formulated these 21 very famous NP complete problems. And there's a guy, Andrew Lucas, has this paper called Ising Formulations of Many NP Problems. So if you take a look here, there are all these problems like exact cover, vertex cover. I think max cut is also in here as well. Maybe not, but it basically tells you like, hey, you can take this Ising Hamiltonian format here, and like the paper will show you like here's how you can translate from these NP complete problems to the Ising format. And once again, what the hope is that if there is a reasonable speed up from doing quantum annealing and the Ising Hamiltonians, then hopefully that will benefit us as we're trying to find solutions to these NP complete problems. Although he does point out, and this language here is a little complex, like not lead to Landau-Zener transitions, and even I don't fully know what a Landau-Zener transition is, but there is this is trying to point out, like what I mentioned earlier, is that there's a dependency on the size of the energy level between the lowest level energy, which is your solution, and then the highest level energy, and that can sometimes not spell good news for when you're trying to find a solution to your problem. But I just wanted to bring up this paper as well. Like this is something I would strongly encourage you guys to read. Very readable. There's no crazy math here other than like some summations. And if it's any reassurance to you guys, I was pretty lousy with math in high school. I remember getting I think a B- in a course, and then I got a C in middle school in pre-algebra. So it's been quite a journey for me to improve my math skills here. But that brings me to the cherry on top is I know the talk promised topological data analysis and the graph isomorphism problem. The TDA I didn't have enough time to prepare, but I did want to show you guys the crux of my work at this startup is that I've implemented the graph isomorphism problem on one of these D-Wave machines, and it's kind of cool how it actually works. And it's a pretty clever solution. So let me go back just very quickly. I know I have oh gosh, I only have 5 minutes here, so I'll keep it within bounds here. The idea behind the graph isomorphism problem, so it's called GI, is pretty simple. Let's imagine you give me these two graphs. I mean this is a trivial example because the shapes kind of give it away. But let's say these vertexes are A, B, and C, and this is 1, 2, and 3. The graph isomorphism problem is asking you to find the following. It wants you to find the mapping between each of these vertexes to the other vertex in the other graph that preserves the edges, that preserves the edge structure. So what I mean is, like, I can come up with one right now, right? So let's say A is mapped to 1, B can be mapped to 2, and C can be mapped to 3. So if I were to replace 1 with A here and so I just replace all these vertexes, we'll notice that the edges between these vertexes are preserved. So these graphs are proven to be isomorphic to each other. That's the graph isomorphism problem, is can you determine if two graphs are next to each other? Now, here is the very interesting thing about this problem. This problem, if I were to ask you guys, like, I mean, here you can put it in chat. Do you guys think this problem is P or NP? If you don't know what P or NP is, that's fine. But for those of you that do know, do you think the graph isomorphism problem is P or NP? Like, just put it in chat, or just guess. Well, I'll give you the benefit of a doubt, and I'm going to assume that your silence means that it's neither, and you're right. The graph isomorphism problem is not P, and it's not NP. In fact, it sits in between P and NP, in that there are certain graphs that we can find the isomorphism in P in polynomial time, but then there are graphs where we cannot find a solution in polynomial time. It takes an exponential or more than polynomial amount of resources to find it, although we can still verify the solution, I think, in polynomial time. So it sits in its own region. So it's very possible that my work and the work of Kalud, Hua, and Deneen, so those are the authors of the paper that I showed a little earlier here. Oh, not here, sorry. It could be possible that there is an efficient algorithm for normal computers, in which case the quantum annealer is not necessary. And if you guys have read Mike and Ike, so That's basically the textbook by Nielsen and Chuang. There's a very famous section where they say, like, look, we still don't know, if quantum computers will, beat like every single problem that we see. And, the graph isomorphism issue might be one of them. But what I want to point out in my last minutes here is how intuitive, or like it's not that painful to understand what exactly this QUBO is doing to calculate the graph isomorphism. So this is the overall formula. You notice there are two terms here, h sub x and then p sub p I comma j x. And the way you think about QUBOs and quantum annealing in general is you define your problem in terms of constraints. So remember the protein folding problem. I mentioned this amino acid likes to be with this amino acid. This amino acid does not like to be with this amino acid. So you don't define your problem in terms of how you do it. You define the problem in terms of its constraints. And if you take a college course, you'll take programming languages and you'll learn about languages like Prolog. I think back in the 80s there was this whole idea of logic-based programming where you would define a problem in terms of like, here is what the solution should look like. Like a boy has these features, a girl has these features. It was defined logically. And that turned out to be kind of a fluke. Nobody uses Prolog anymore. It's kind of it's dead. But what I digress. The idea is that for quantum annealers, and QUBOs and these Isaac Hamiltonians, you're defining a problem in terms of its restrictions. So for the graph isomorphism problem, one of our restrictions is it's a bijective function. So bijective function is fancy for one-to-one mapping. So that means like if I have stuff in my domain and stuff in the function output, only one thing in the input should map to one thing in the output, one and only one. So there should never be a case where two things in the input map to one thing in the output. So this h sub x term here, or h of x term, enforces this constraint. And then this is a little harder to explain, but the basic idea is it wants to make sure that if you have a valid bijective mapping, that the edges are preserved as well. So this is another constraint. So you got to recognize that the language we're using here is in terms of constraints. Like, what do I want? What do I not want? This paper, by the way, once again, for all of you watching this, I strongly recommend you read. I've actually reached out to Richard Hua before. I told him I developed this software, and he was really happy to hear it. And he even, I think he even cites my work in like an update to his original paper, which is really cool. I don't know about you guys, but that gives me a lot of much needed self-esteem boost. Yeah, this is what I mean by a very readable paper is if we look here, there's a whole walkthrough. Like, I don't know about you guys, but like math textbooks are horrendous at like giving you like step-by-step instructions. This paper has step-by-step instructions. So if you want to like maybe mess around with this QUBO, then this is your kind of one-stop shop. And my last closing remark is, let's see if I can pull it up here. Oh, here it is. If you want to actually look at like an example of how maybe this QUBO is implemented and how to get it on a quantum annealer, this is a GitHub repository that it's from my company, but I essentially implemented the paper there as this library, and you can kind of see. Oh, actually, let me see if I can give you guys an example here. Let's see, matrix form. Excuse me. You can see like I have these two graphs here, and this is just a pretty trivial example to get the idea across. But you can run it on a quantum annealer. In this case, I'm just running it on the simulated annealer. When I ran this on an actual, because I did this on AWS Bracket, the performance was not great for obvious reasons. But here you can see what I was talking about by the mapping. So vertex 1 maps to vertex A, vertex 2 to B, 3 to C, 4 to D, 5 to E. And then there are some more. Oh, you can also do, if you relax the constraints a little on your QUBO, you can do subgraphs. So subgraph is like an embedding in a bigger graph. And you can see I've highlighted it here. I want to get this triangle in this bigger graph, and we can do so here. So this is fully open source code. Feel free to like fork it, mess around with it, break it, do whatever with it. Although I do want to caution is that it's GPL 3.0. So what that means is if you use this code in a project, that project you're using it has to be open sourced as well. But yeah, that's kind of my whirlwind tour of the of this perspective in quantum annealing, and and I certainly hope it was somewhat fruitful. I recognize it's a little messy. I'm willing to blame part of that on my lack of sleep from that senior design project, which after this lesson, I'm still going to have to work on. But you know, I want to extend my gratitude to Anisha and Tanisha as well for organizing this, and you know, for those of you that are high school students, I mean, hats off to you guys. I really wish you have no idea how much I wish I knew community was or I wish community existed, you know, when I was a high school student, because I only started getting into quantum computing I think around my second year of college. So it's really phenomenal work the community team is doing here. I'm super grateful to be able to give this lesson and kind of hopefully, you know, you guys might learn a thing or two. I have learned a thing or two. And yeah, if you have any questions, you know, feel free to ask in chat or unmute yourself. But otherwise, you know, thank you so much for your time. I really appreciate it.
Does anybody have any questions? So do you want to give your information in case anybody would want to reach out to you for more questions or anything?
Yeah, sure thing. I can put that in chat here. Let's see, I think my email is, I know you guys are getting a laugh here because like why is this dude like struggling to remember his email? Because I have 4 of them. I have one for the club, one for my workplace, one for school, and then one for my personal. I'll give you my let's give you my personal email, John Yell. Yeah, if you have any questions, feel free to shoot me an email. I'm pretty responsive. Maybe not for this week because of the senior design project, but you know, I love being able to answer questions. So by all means, if there's anything, even if it's not quantum annealing related, shoot me a message.